Hello and welcome to the fifth session of NPTEL course. So the course is Advanced Thermodynamics and Kinetics. I am Umar Rashid. I am currently doing my PhD in Indian Institute of Science, Bangalore, and here I am every Friday from 6 to 8. I am giving an assignment solution session every Friday, where I am showing you how to solve some of the questions from the assignments, and I revise in the meantime. I revise some of the topics that are necessary, and I go through the equations that are necessary to solve those assignments. Okay, so this is the fifth session of the NPTEL of this session. Okay, so first of all, I'll just show briefly what we have done in the previous session. Okay, what are the questions that we have solved and some of the basic concepts. And because last time once we had solved only 5 questions, there were 5 questions remaining from the last topics, that is related to fluid dynamics. Okay, so let me go very quickly to it. Okay, so yeah. Okay, so these are the questions that we were trying to solve the last session, during the last fourth session. Okay, and we have actually solved it from question number 1 to question number 5. These questions are related to fluid dynamics, and they encompass the topics like diffusion, viscosity, mean free path, and everything. So, I'll first show briefly what are the questions that we have sort of shown last time. Okay, okay, so in the session 4 we have these are the topics that I revised briefly. First is the refinement of the mean free path, because we were calculating the diffusion coefficient which is related to the mean free path. Okay, so since we calculated the diffusion by using the average speed, which is not actually correct, so we have to use the relative speed, because the molecule of the gases are always in random motion, and we always have to relate the relative viscosity between them. Okay, then we have I showed how we can change the average mean free path to the relative velocity, and from that relative velocity we got to know about some of the expression that is actually shown here, that I have discussed in the previous lectures, whose links and as well as this PPTs are available on the YouTube and the Google Drive. Okay, so now then I have told briefly about the diffusion and some of the equations related to the diffusion, how the diffusion can be related to the mean free displacement. Then what is the relation between the diffusion coefficient and the diffusion flux? This will be using today this equation. Okay, then what is the difference between a laminar flow and a turbulent flow? Okay, and what is the viscosity and what is the viscous force that is generated? Okay, how the viscosity can be related to the average how the viscosity can be related to the molecular diameter, and using the molecular diameter we can calculate the viscosity. Okay, and how the viscosity changes as a function of the temperature. Then I have shown you the flow resistance of a tube, effective flow, then Stokes law, and how different diffusion, how the equations are the fundamentals of the different diffusions, like momentum, energy, and the mass transfer quantities, they look actually similar. Okay, so that was our end, and we have shown that was our fourth session. Okay, so using those equations we have solved some of the questions. Now in the fifth session will be actually, so we have already solved from we have already solved from question 1 to question 5. Okay, so from today we'll be we have solved from question 1 to question 4. Okay, we'll be solved from question 5 to question 10 today. This is related to the fluid dynamics also. Okay, so just a second. Okay, so now and then if the time persists, we'll go to the next topics or the next assignment questions, which is related to the reaction kinetics. Okay, the rate of the various reactions. Okay, because the thermodynamics will tell us, this course is regarding the thermodynamics as well as the kinetics, as we know that okay, so I'll brief. This course is about the thermodynamics. Okay, so you all might be knowing that thermodynamics tells us the feasibility of a reaction. Okay, so feasibility means it will tell us if a reaction is going to happen or it's not going to happen. Okay, but it doesn't tell us how the reaction will proceed or what will be the rate of the reaction. Now those concepts are given by the kinetics. Okay, rate of reaction, rate or mechanism of a reaction. Okay, so let us go to the question number 5, which I have put in this. Yeah, so question number 5: if a mean free path of if the mean free path of oxygen is 4 into 10 to the power minus 7 meter and the average velocity is this, find the value of diffusion coefficient of oxygen in this, and this is the molecular diameter is. So we have been given molecular diameter, we have been given molecular diameter, we have been given the mean free path and average velocity. So we have to find the diffusion coefficient. If you will go through my previous 2 lectures, I have shown you how the mean free path is correlated to the diffusion coefficient and the diameter. So we'll directly use the equation to solve the problem. Okay, so let us proceed with the problem. I will write here. So we have our question 5. Okay, so I already showed you from the in the previous lecture number 3 and lecture number 4 that how the diffusion coefficient is related to the mean free path. So one of the equation I have shown you is diffusion. All these equations are given in the presentation number 3 and presentation number 4 that are uploaded in the Google Drive. The links will be available in the Excel that has been shared by the NPTEL. Okay, so we know that the diffusion coefficient, which is given by D, is given by 1 by 3, while this is an average velocity and lambda is the mean free path. So here V is the average velocity and lambda is mean free path. Okay, so yes, so average velocity and the mean free path. So this we already know. Now we know that what is the in the question the average velocity is given. Okay, so this average velocity is meters per second. The average velocity is like in gases. If we say that there are 3 different kinds of the velocities, right? As I have told you in the previous lectures that there is I can show here average velocity, there is root mean square velocity, and there is most probable velocity. So this average velocity is under root 3 RT by m. Root mean square velocity sorry, average velocity 8 by pi RT by m, root mean square velocity is 3 RT by m, and most probable velocity is 2 RT by m. Okay, so if we go which is the highest, or if we can plot a okay, if this this is the Boltzmann's distribution. Okay, I will write as f, and this is the velocity. So we will have three kinds of the quantities. One is this, another will be here, another here. So actually I should write it differently. It is actually this way, not exactly, but you can write it this way. Okay, so this is our here, this is the Boltzmann's function v dx. This is our velocity. So we have three quantities. One is here, another is here, another is here. Okay, so this is the root mean square velocity, that is 3 RT by m. I will write 3. This is the average velocity, okay, that is 8 by pi. Okay, and then this is the most probable velocity, which is 2 RT by m. Okay, so here we are concerned with the average velocity. Okay, so we know these quantities, right? So now in the question we have been given three things. One is most probable velocity, the second is lambda, that is the mean free path. It is given as 4 into 10 to the power minus 7 meter. Okay, so we'll use the above equation, that means d is equivalent to 1 by 3 v most probable velocity multiplied by lambda. Okay, that is given by 1 by 3, most probable is 630 meter per second multiplied by 4 into 10 to the power minus 7 meter. Okay, so if we calculate it, we'll get 8.4 into 10 to the power minus 5 meter second per second. So that is our answer. Very easy to calculate. You just have to don't need to remember, just get the physical significance of different equations, what the equations are related, and by this you can solve the question. Okay, let us go to the question 6. Okay, so the question 6 is, for a wall of dimension 5 meter into 7 meter, what will be the rate of heat loss? I'm recording here. What will be the rate of heat loss if the wall is insulated with fiberglass? The thickness of the insulation is 20 centimeter and the temperature difference on the two sides of the walls is 15 Kelvin. Take the coefficient of thermal conductivity to be this. So this is regarding the insulation. So if we see, like in majority of the foreign countries where there is too extreme cold, or it can be too extreme heat, what people will do is they'll just create the two walls, they'll just create the two walls. So this is, for example, if these are the two walls, then what they will do is, since these walls are made of wood or something, they have high thermal conductivity. As a result, the outside temperature or the inside temperature, it will go out, or they'll feel cold. So what they do is they fill up with the fiberglass. Okay, so if this is a fiberglass, so what happens is this acts as an insulation. It does not allow the heat to flow in or to flow out. Okay, so this insulation helps to keep the warm. This is the this is the principle in which we keep all the material, like insulating materials, like we have thermos, like while we keep heat for longer period, this warm tea or warm food for a longer period of time. So there you have a covering and you have a very high thermally insulating material in between the walls. Okay, so as a result it will not allow escape of the heat, or if you want to put too cold, it will not allow the heat to come inside. Okay, so the one of the best insulating material for building material is fiberglass. Okay, so that fiberglass. Okay, so here the question is regarding that we have to show that how much heat will be lost when a particular fiberglass is. So for that we'll actually be using the Fourier transform. Okay, sorry, the Fourier's law. Okay, so if you might have revised it in your course that first Fourier's law. So that tells us about the flux of energy. That means energy of the total energy that has been flowed per unit time, per unit space. Okay, so flux of, if we denote it by Jz, it will be given by minus K, but K is our dt by dz. Okay, where K is thermal conductivity. Okay, and this dt by dz is gradient. So it is actually the gradient of temperature as a function of length. Okay, and this is the negative of the gradient. Okay, because we know that delta T is temperature difference, and this is the thickness. So here delta Z is thickness of insulation. Okay, so if I will write here T1, T2, and from here to here it is dz. Okay, then delta T will be T1 minus T2, and this delta Z will be thickness. For example, we will call it as D. Okay, so that is now. Also in the question it is given that what is the temperature difference between two, what is delta T. Okay, temperature difference, it is 15 Kelvin, and the thickness is 20 centimeter, or we can write as 0.2 meter. Okay, so we'll first calculate the gradient, actually the negative of gradient. Okay, so this is our gradient. Okay, what will be the total heat loss? Total heat loss will be heat loss per unit area multiplied by total area, right? So heat loss per unit area is given by our heat flux, because it is a heat loss per unit area per unit second, and then total area we have to calculate. Okay, so we have to calculate what is the total area. Area they have given is 5 multiplied by 7, length in the breadth 35 meter square. Okay, so total heat loss will be equivalent to 35, that's our area, meter square, multiplied by 7.5 into 10 to the power minus 2 per meter per Kelvin. mm, multiplied by, so what I have derived, got this equation is total heat loss will be, as I told you, it will be JZ multiplied by A. Now JZ multiplied by A. Okay, so JZ will be given by minus K dt by dz multiplied by area. So we put all those values. Conductivity is given by this, K is given by this, dt by dz is given by this, and the area is given by this. So that's as simple as that. Then we calculate the total. It will become 196.875. okay, also we have to find the series. We have to find the unit. Okay, so we know that this K Kelvin and per Kelvin will cancel, meter and per meter will also cancel. Okay, meter square, meter per meter and meter square will cancel. Okay, so what we are left with? We are left with watt. That is the actual form of energy. So the total heat loss will be this much. So that solves our question. Okay, so all the questions are easy. The thing is, we just have to use a proper equation and see how are the fundamentals that are relating to it. If we know a little bit about them, we can solve them. Okay, so that is the whole crux of the story. Now we'll go to the next question. Okay, the next question is regarding okay, consider two molecules A and B in which the diameter of A is greater than diameter of B. Which molecule will have larger coefficient of viscosity? Okay, so the question is regarding the two molecules in which diameter of A is greater than diameter of the B. So I have already shown you the equation which relate coefficient of viscosity with the molecular diameter. We simply use that, and from that we'll calculate. Okay, so I'll write question probably 7. Okay, I already showed you that this viscosity coefficient if eta is our viscosity coefficient, it depends upon our average velocity. Okay, molecular mass 3 under root 2 pi into d, where d is molecular diameter. It is actually physically, intuitionally also, that as the molecular diameter, it will face more drag. So since the viscosity is a drag, the viscosity coefficient increases. Okay, so from this we can see that eta is directly proportional to 1 by d. Cool. Now from the equation it is shown that diameter of A is greater than diameter of B, right? So if the diameter of A is greater than diameter of B, what we'll do is we'll write NA is directly proportional to 1 by dA. Okay, and B is directly proportional to 1 by dB. Okay, so if we divide NA by NB, it will be equivalent to dB by dA. Okay, if dA is greater than dB, that means this is greater than this, then NB is greater than NA. Eta. Okay, so the viscosity of B, obviously, whose diameter is larger, the viscosity coefficient will be smaller. Okay, because of this equation, because of this equation. Okay, this proportionality. So that solves our question. Now we'll go to question number 8. Which of the following relation is correct for viscosity coefficient of thermal conductivity? Okay, there was a question, I have forgot to write the options. Okay, so it is regarding the viscosity coefficient. It is regarding the thermal conductivity, that how the thermal conductivity is related to the average speed. Okay, so we'll so how you will solve the question is, what you have to do is, you need to, I'll write solution 8. Okay, you need a fundamental equation, like not fundamental but thermal conductivity equation. Okay, so we know that thermal conductivity is given by this relation I have shown. This is thermal conductivity is given by average velocity, CV, heat capacity at the constant volume for gas. Okay, then 3/√2 pi constant, d square is diameter, and n is Avogadro's number. Okay, so K, thermal conductivity, is directly proportional to the average speed. Okay, average speed, but we know that average speed is given by √8 by pi RT by m, where m is molar mass. So V is inversely proportional to molar mass. That means K is inversely proportional to molar mass or molecular mass. Molecular mass as m into n a. So we can write K is directly proportional to 1 by m, where m is molecular mass and this m is molar mass. Okay. Okay, so what we'll do is, we know that helium gas is lighter than argon. Though if we see the periodic table, we will see helium, then helium neon, argon, krypton, radon, like this. Okay, so since the molecular mass increases below, so what will happen is, helium is lighter than argon. So what will happen? Average speed, if we say average speed of helium should be then greater than as compared to that of argon. Okay, when the average speed, which implies that thermal conductivity of helium is greater than thermal conductivity of argon. Now this is highly implied. If a molecule moves very fast, so what will happen is, it will take it moves very fast. That means the average velocity is very high. So that means that it will has higher moment, so it will carry more heat from one part to the another part. So that is why helium has thermal capacity more than argon. Okay. Also, if we say that nitrogen is lighter than argon and CV of nitrogen is higher. Okay, now we have another question. This equation does not only if we see this equation, okay, it includes thermal conductivity as a function of heat capacity at constant volume, as well as Na, as well as this average velocity. Okay, so previously we had both monatomic gases, so Cv is constant, Cv is almost same for both, but here now we have nitrogen as a diatomic gas. When nitrogen is diatomic, Cv will be higher, okay, because it's a diatomic. When Cv will be higher, then because of that, what will happen is that thermal conductivity of the nitrogen will be higher as compared to thermal conductivity of argon, even though m, that means the molecular mass of argon, is greater than molecular mass of nitrogen. Why? Because K is directly proportional to Cv, why K is thermal conductivity. So these are the two statements that are correct regarding the thermal conductivity. So we have to remember thermal conductivity depends on we have to remember that thermal conductivity depends on uh, heat capacity. Okay, so heat capacity is how much amount of the heat is required to increase the temperature of 1 mole of a substance through 1 degree. For example, if we have water at 15 degree and then we want to change it to 16 degree, and how much heat we have to give, so that is a thermal conductivity of water is very high. That is probably why it is most abundant in the nature. Okay, we use water everywhere, like in boil, and it stores a lot of the implications are the materials or the liquids or the solids which have higher thermal conductivity, they can store more heat. Okay, so more storing of the heat they can is useful in certain cases, like for example in plants, in animals, even though the external temperature is increasing, because water can absorb a large amount of the heat without changing much temperature because of higher thermal conductivity. As a result, we'll have higher water can store higher amount of the heat. Okay, so that is the reason the water is abundant in the nature. Okay, so K is directly proportional to heat capacity. K is also directly proportional to average velocity. Okay, so average velocity, and since the average velocity is inversely proportional to molecular mass. Okay, so lighter the element, higher will be the heat capacity. Why? Because the average speed will be more. Okay, and it also depends upon the molecular diameter. K also depends on molecular diameter. Okay, so smaller the molecule or smaller the atom, higher will be its heat capacity. Okay, so these things, this is just by the intuition, you can also remember it. Okay, now we'll go to another question. We'll have question number 9 now. Okay. What will be the concentration gradient of 6 stars in units of molecular mass at? Okay, so what we have to calculate, we have to calculate the concentration at 6 stars. Okay, okay, what we have been given the pressure per centimeter. Okay, what we have to calculate is, we have to calculate the concentration gradient. Okay, and the temperature is also given. So we'll go to question number 9. We know that. Okay, so if we PV is equivalent to nRT, the ideal gas equation we'll use. One minute. Okay, so doing a little rearrangement, what we'll arrive at is P is equivalent nRT by V. Okay, what we have to do is we have to convert the pressure gradient into the number density. Okay, how can we convert? So we'll write that pressure gradient okay, so how? See, we have a pressure. Okay, a pressure gradient. Now we want to convert into number density gradient, n by v. Pressure gradient is uh, okay, so we have this equation. Okay, so what we'll do is we'll write P by some area, because it is pressure per unit area, pressure gradient. Okay, is equivalent to n r t by v. We have to multiply a here also. So this is pressure gradient, will denote it by P G. Okay, is equivalent to n r t by v a. So P G by R T will be equivalent to n by V A. Okay, where n by V A is number density. Okay, by A, that is, so this is a pressure gradient. This is if we divide pressure gradient by RT, what we can, this is n by V is number density. N by V is number density, A is area. So N by V A will be number density gradient. It should be, since it is a gradient instead of A, so A will not be a area. A will be sort of, we'll write as length. Okay, where A is length. Okay, now we know this equation. Okay, so what we have to do is we have to so the number density gradient. Okay, so how we will represent is we will write n by v is given by p by r t. Okay, that is given by dz star by dn star by dz. Okay, so this is number density gradient. So how we'll write how we'll calculate number density gradient is dn divided by dz will be equivalent to, what is the pressure gradient? It is 60 torr per centimeter multiplied by 1 atmosphere by 760 torr. How we want to convert 1, because we know that 1 atmosphere is 760 torr. So torr is actually 1 torr. If we say it is 1 mm Hg. Okay, so then what we have to multiply it with, since we have to calculate number density, we have to multiply it with Avogadro's number. So it will be molecules per mole. Okay, then there should be divided by 0.0 0.082, the value of R and temperature T, which is given. Okay, what we'll do is this Kelvin and this Kelvin will go, per mole this will go. Okay, this torr and torr will go, this atmosphere will go. Okay, if we want to now we'll go further. 0.4755, we know that 1 liter is 1 decimeter cube, that is given by 1. Deci means 10 to the power 1. Okay, 1 into 10 to the power minus 1 meter, that is 10 to the power, and this is cube, that is 10 to the power minus 3 meter cube. Okay, so put that value, will determine the number density to be equivalent to cool. So what will calculate? 47.55 by 24.6 into 10 to the power 26 molecules per meter cube per m per meter. So our number density dn star by dz, number density gradient will be 1.93 into 10 to the power 26 molecules per meter cube per meter. Okay, so if we know that this dn, okay, it is n by v, so the units of dn will be molecules per unit volume, right? Molecules per unit volume. And the value of dz will be meter. So the total unit of number density gradient will be molecules per meter cube and then per meter. Okay, so that is what has been asked before in the question also. What will be the concentration gradient of this torr per centimeter? Pressure gradient was given in units of molecules per meter cube per meter at 300 Kelvin. Okay, so we solved that equation. Now let us go to the 10th. For a value of concentration gradient obtained in the above equation, find the number of oxygen molecules diffusion to carbon dioxide per second and crossing an area of this. Take a diffusion coefficient. Okay, so what we have to see is the relative rate of diffusion of oxygen to that of the carbon dioxide through the cross-sectional area at a particular temperature, where the diffusion coefficients are given. Okay, so if you remember the equations that I have shown in the previous lectures, we can solve that easily. Okay, so we have question number 10. Okay, so the question number 10 tells us we have to write the diffusion numbers that are crossing the area. Okay, so For that, I already have shown you that flux is given by d, that is the diffusion coefficient, dn star by dz. Jz is flux density, d is diffusion coefficient, and dn star by dz, that we have derived in the previous. It is number density gradient. Okay, so we have to calculate Jz, that is given by minus value of d this, that is given, multiplied by dn by dz. We have calculated that 1.93 into 10 to the power 26 molecules per meter cube per meter, right? Okay, so using we can calculate this to be 3.09 into 10 to the power 21 molecules per second per meter square. Number crossing the area of, what will be the total number that are crossing this area? It will be directly area, because flux is numbers crossed per unit area, so it will be area multiplied by flux. Okay, area is 0.3 meter square, flux is 3.09, 10 to the power 21 molecules per second per meter square. So the value will be, I will write capital N as number crossing, 9.27 into 10 to the power 20 molecules per second. So that is our answer. Okay, so what we have just used, the equation for the flux and flux density, correlated it with the number density which we have calculated in the previous step, and then from that we can calculate the what are total number of the molecules that are crossing. Okay, so this completes our assignment number, this assignment, that was assignment number 2 or 3rd. Okay, this was regarding the fluid dynamics. Okay, now we'll be taking another question, different questions which are related to the kinetics. Okay, chemical kinetics. Okay, so the chemical kinetics, that's how a particular reaction rate and what is the mechanism. As I have told you, the thermodynamics tells us the feasibility of a chemical reaction, whether a reaction will take place or whether a reaction will not take place, but it does not tell us how much time will a particular amount of the reactants will get converted into a particular number of the products, or which products are formed. Okay, and how the products are formed. Those are told by the chemical kinetics. Okay, so our next batch of the questions will be from the chemical kinetics. Okay, so the first question is okay, 1 minute. Okay, so we have to go so the question is saying that the decomposition of nitrogen monoxide bromide into NO and Br2 has a rate constant of this. Okay, so we have been given the rate constant. The order of the reaction is, okay, so you should know that first we'll just briefly we'll write a different assignment. Okay, first I'll tell you different about a rate of a reaction. Okay, so rate of a reaction is how much amount of the reactants are converted into products per unit time. Okay, so it is also we can determine in terms of the products how much amount of the products are formed per unit time. So the rate of the reaction will always be mole per liter. This is the concentration, this is the concentration iteration per unit time. Okay, per second, mole per liter per second, because the rate of a reaction is given by rate of change of concentration, that I will represent by this to that of the T. For example, if we have a common reaction, A is getting converted into B, so we can determine the rate of reaction. Rate of reaction will be equivalent to change in the concentration of A per unit time, okay, or change in the concentration of B per unit time. Now if we say that change the concentration, but we already know that this rate is the concentration of the A will get decreased as a function of the times, but the rate of the reaction cannot be, so we'll put a negative here. Okay, so for reactants it is negative, so this is, and for both these the units of the rate of the reaction is concentration per unit time. So concentration can be determined in partial pressures, and so here it is mole per liter per second. So that is the unit of rate of reaction. Cool. Now this is a very simple reaction where A is getting converted into B, but there can be other reactions like very complex reaction where A plus B is getting converted into C plus D. So for that, the rate of a reaction, which I will represent like rate, it can be written as dA by dt. We know that A is a constant, so I will write minus because it's a reactant. It should be equivalent to rate of B. Now remember, this is a very simple reaction where one molecule of A reacts with one molecule of B to produce one molecule of C and one molecule of D. Okay, for a complex reaction I will show you that we have to divide by stoichiometric constants. Okay, will be equivalent to dC by dt dt by dt. Okay, but for a reaction where small a number of moles of A reacts with small b number of moles of B to give C of C and D of D. What we have to do is the rate will be given by 1 by A. We have to divide it by the stoichiometric constant because it will be consumed that many times. Okay, so then dA by dt 1 by B dB by dt 1 by C dC by dt 1 by D by dt. Now I'm sure that this is very elementary, so you might have read them in your secondary classes. Okay, so now you might have also heard about law of mass action. So it was given by Goldberg and Vegi, where they told that a rate of a particular reaction is directly proportional to the concentration of the reactants. For example, we have a reaction A times A, it gets converted into B times B. Okay, so rate of the reaction is directly proportional to the concentration of the reactants raised to the power their stoichiometric coefficients, like this. For a complex reaction, right, I have shown here AA plus BB is given by CC plus DD. The rate of the reaction will be equivalent to that of some rate constant. Okay, then you have concentration of A raised to the power A, and then concentration of B raised to the power B. Similarly, if the reaction is a reversible reaction, so there are both forward as well as backward reaction, then rate of we will write forward rate, then we will write backward rate. So backward rate of the reaction, this will be forward KB, it will be given by C raised to power C and D raised to power D. Okay, so technically they were first given as active masses, but we are writing it's almost equivalent to that of the concentrations. Okay, so then obviously we write how we can determine the equilibrium constant of these, that we will not go there. Okay, so this is a rate constant. Now we have a different kind of a reaction. So if we have an order of a reaction. Okay, now this is from the law of mass action. It's not always correct. What we have to determine, we have to determine the mechanism of a reaction, and from the mechanism we have to correlate how a rate of the reaction is dependent upon the concentration of the reactants. Okay, it can sometimes be depend also concentration of the products if the product is interfering. Okay, so what we have to do is order of a reaction. So simply, if I will write as rate of a reaction whose units are mole per liter per second. Okay, this is the rate of a reaction. Okay, it is equivalent to K times, K is the rate constant, concentration of something raised to power A. Okay, if A is 0, we term this reaction as a zero order reaction. Okay, this is a zero order reaction. That means the rate does not depend upon the concentration of the products. Okay, it will go on. Okay, so similarly, if this is A equivalent to 0, if A is equivalent to 1, then it can be a first order reaction. Similarly, we can have A is equivalent to 3, a second order reaction, and 2 second order reaction. Similarly, A can be 3, a third order reaction. Okay, so this is a third order reaction. Now we have to find we know the units of concentration. Okay, units of concentration are mole per liter. Now for different kinds of or different types of the reactions or different reactions with different orders, they will have rate constant with different units. For example, if we say that we know that rate it is unit is mole per liter per second for a zero order reaction. Since A is 0, so the concentration that will become equivalent to 0. I will write mole per liter raised to the power 0. Since anything raised to the power 0 is 1, so the units for a zero order reaction are mole per liter per second. Cool. Now if this is what this is a zero order reaction. I will write here 0. Now we have a first order reaction. Now for first order reaction, what we will do is, we know there also that rate whose K mole per liter raised to power 1, right? Now this by this we'll write K is equivalent to, this will get cancelled, this will get cancelled, this will get cancelled, this will get cancelled. So in nutshell, what we can know, the it will be per second. So for first order reaction, the rate constant will be per second. Okay, similarly if I write for second order reaction, rate has the same units as are told you before, K, then we'll have mole per liter, it is square. Okay, now since it is square, it will be given by K mole square liter minus square mole per liter per second. Okay, so the K will be given by the units of K will be mole per mole liter per second. Right, so this is zero order, first order. So if we know the rate constant units of a particular reaction, from that we can predict that what is the order of a reaction. Okay, so in probably we can write for any order reaction, the units of K will be equivalent to mole liter second. Now we know that from 0 second first order as well as the second order, the second does not change, so second will always remain in -1. Okay, now for first order reaction, zeroth order reaction, it is 1. Okay, for first order it is nothing, for second order it is -1, so we can write 1 minus n. Okay, then L has -1, nothing, we can write n -1. This can be this formula. Just a second. Okay, so this equation, using this equation we can determine the units of rate constant of an equation. Now if we go to the question, what it tells is that close this. Now question is from the question we came to know that the units of rate constant are mole per mole liter per second. Okay, so if we correlate this to this, so that means this is a second order reaction. Okay, so that's a second order reaction. Oh, that is very simple. So you have to determine the order of a reaction from the rate constants. Okay, now we'll go to this was the question 1 of the new assignment. Now we'll go to question 2. During the sulfonation of naphthalene at 80 degree, the major product former is 1 naphthalene sulfonic acid. Okay, while at at 160 degree, the major product formed is 2 naphthalene sulfonic acid. Which of the following can be true? Okay, so the reaction is about if we take like naphthalene, that is like this. Okay, so this is naphthalene. We do the sulfonation. Okay, so two products can get formed. This product and this product. Okay, so we have 1 naphthalene sulfonic acid and 2 naphthalene sulfonic acid. Now the question is, at 80 degree 1 naphthalene sulfonic acid is formed, and at 160 the 2 naphthalene sulfonic acid is formed. Now what is the inference that we can get from it? Okay, so this product is formed majority at 80 degree. At 160 degree this product is formed. Okay, now the answer to this is C. I'll also write here, since product B is formed at higher temperature, that is 160 degree Celsius, which means it requires a higher activation energy. But it is also more stable than A after this activation energy, so we can say that B is thermodynamically controlled product, while okay, so we know that the B is formed at very high temperatures, okay, 160 degrees. So this B is formed at high temperature, so that means it requires more activation energy. So activation energy is the extra amount of the energy that is required for a reactant to react to form the product, okay. Not necessarily it will form the product to go to a transition state, okay, to the highest activation energy. Now we know that this only is getting formed at 160 degrees Celsius. That means that it requires higher activation, but this is also more stable as compared to this. So as a result, we can say that B is kinetically, it's a thermodynamically controlled product, okay, thermodynamically controlled product. But since A forms at lower activation energies, thus it is a kinetically controlled product. So I'll give a brief description, okay. So for example, this is the energy, okay, this is the energy. So what will happen is that, and we have this and we have this, okay. So what it is like, for example, if at this point we have reactants, okay, at this point we have products. So what will happen is that reactant will have some of its own energy, okay. For example, if this is 0, so this is some energy the reactant has, that's called as a 0 point energy. I'll write that as an E, okay. Now if we see that from here up to here, if we say that total energy is E double star, but E double star is the total energy that is needed for this formation. So it forms some like this, I'll say it forms an activation complex. That means E double star will be the total energy. It will be equivalent to what will be the energy plus E star, okay. The E star is the energy from here to here, okay. So E star is activation energy, so E star is the activation energy, okay. This is activation energy, okay. So similarly, now what I am saying is, so this is the extra energy that is required for to form a complex, okay. Now this is E, and this is some, we can say this is a reaction coordinate on this side, okay. Now if we have two products that are formed, okay, one product and the second product, so here what we can show you, here we have the reactants are at the same side. So we have naphthalene, they are at the same side. Now we have two complexes here. One, the activation energy is this much, second, the activation energy is this much, okay. I'll write this activation energy as EA, this activation energy is EB, okay. From here the B is formed, from here A is formed, Okay, now what I am trying to explain is what is a thermodynamically controlled product and what is a kinetically controlled product. Okay, now you see this if we see not much activation energy is required. So once a product is formed, the lower kinetic energy product is formed. It is not also more stable as compared to that of the B, but the activation required is low. That means it is kinetically favored product because the activation energy is less as a result, but it's not thermodynamically favored product, because thermodynamically favored product will be the product which has where the delta E of the reaction is maximum. That means that product where the delta E is maximum, that product is thermodynamic driven product. Okay, that product, this is EA, this is EB, that product where E star, as I told, E star is activation energy, is lowest, that product is kinetically driven product. Okay, so we have two kinds of the products. One is thermally driven product, one is kinetically. Now kinetically driven products are formed at lower temperatures. Why? Because less activation energy is needed. Thermodynamically driven products are formed at where more rate of the reaction is. So if we say the rate of, if we say the reaction total reaction energy change, that means the 0 point energy of E of products minus E of reactants. Okay, that means delta E of a reaction. Okay, it is tells us about the thermodynamics. Okay, so this tells us about the thermodynamics of reaction. Okay, but if it is regarding the E star tells us the activation energy. It tells us about the kinetics of a reaction. Okay, so at a particular time, if the reactions are driven very fast, okay, or at lower temperatures, the kinetic products are formed. But once the reaction is given enough time to enough time, then the kinetic product will get changed into thermodynamic product, or it might not be the case. Okay, so if the reaction has enough time and enough energy to proceed, that is, it is not kinetically hindered, then always a thermodynamically stable product is formed. But if the reaction doesn't have enough energy to proceed, then thermodynamically driven then kinetically driven product will be formed. So that is the main crux of the story. Okay, so this constitutes our second. Okay, now we have question third. Question third is, we have a reaction that's a consecutive reaction. So it is like A is getting converted into B and B is getting converted into C. Okay, for A to get converted into B, the rate constant that I have told you, what does it mean? It is directly it is given by K1, and from B to C it is given by K2. Okay, A0 means the rate, the concentration at the initial, once the reaction was started, it was 50 mole per liter. K1 is 4 per second. Okay, since it's a first order reaction, so it is 4 per second. K2 is 3 per second. We have to show that what is the amount of the C that is formed at 0.5 seconds. Okay, so we have been given a consecutive reaction. A gets converted into B, B gets converted to C. Initial concentration of the A is given by using the two rate constants K1 and Q2. We have to show what is the final product after 0.5 seconds. Cool. Okay, so it's a very simple. We just have to use the concepts of the how the chemical reaction is related. Rate constant is equal to the reaction, and the reaction rate we can determine. Okay, somewhere I have written other things. Where are those? What? I think I lost the progress for A and B. I think so. Most probably I lost that. Okay, so I have already explained the concept of this kinetically favored product and thermodynamic favored product. Okay, so as I already told you, I'll just make it once so that you people will have something to read. This is E, this is our reaction coordinate. Okay, so we have a hump like this. Okay, if this is reactants, this is energy of the 0 point energy of reactants, 0 point energy of products. This is the total energy that is for an activation complex like R star, I will write. Then E T is equivalent to E 0 point energy plus the activation energy. Okay, where E dash is the activation energy. Okay, also we can write delta E is 0 point energy of products minus 0 point energy of reactants. Now I have already told you EA, that is the activation energy. It tells us about a kinetics of a reaction. Okay, and if we have delta ER, it tells us about thermodynamics of a reaction. Okay, so if we have a compound like a reaction where instead of one we have one here and another will have here. Okay, so we have a reactant just like we had a reactant N. This is energy. Okay, we have a product A, we have product B. Okay, the activation energy for this will be EA, the activation energy for another one will be EB. Okay, so also delta E of the reaction will be EB minus N, and delta EB of the reaction in case of product 1 is found, I'll write this B, this I'll write A, will be given by EA minus N. Now if reaction goes very faster, then EA is very smaller than EB. Okay, then A is formed. Now if we see in this system that A is formed, then A is kinetically driven product here. Okay, but if delta ER, we know that for A is less than delta ERB, okay, comma B is formed, then B is thermodynamic stable product. Okay, so we have in this we have a thermodynamic stable product. Now we'll go to question 3. Okay, so question 3 is for a consecutive reaction. Here we have A getting converted into B and then B getting converted into C. So what we have to see is we have to see the amount of C that is formed. Okay, initial concentration of E. So how much will be the amount of C that is formed in this reaction? Is if we see there is no stoichiometric coefficient, so that means one molecule of A, if it reacts, it will give one molecule of B, one molecule of B will give one molecule of C. So we have a straightforward. So amount of the C formed at any time will be, so how much will the amount of the product? It will be, I will write C, it will, the total amount that was present A minus the amount of A that is at a particular time like available, okay, minus the amount of B that is found, because we know that at any time the amount of A plus the amount of B plus the amount of C, it will be equivalent to A naught, to initial amount that we have taken. Okay, so A naught is initial concentration of A. A is concentration of A at time t. B is concentration of B at time t, and C is concentration of C at time t. Okay, we should also remember that at any time initial time. Okay, initial time, since there is no B, so the concentration of B at initial time when T is equivalent to 0 will be equivalent to concentration of C when T is equivalent to 0. They will be equivalent to 0 at time is equivalent to 0. That's when the start of the reaction. So what we'll do is we'll simply write the first order equation. Okay, rate of a first order equation, that is d of A by dt minus is minus k A. Cool. Now since it is equivalent to 1, what we can do is we can write d A by d minus by A, okay, will be equivalent to minus k dt. It will not be, it will be plus, okay, kt. So what we can do is this is equivalent to ln, and from that equation we'll come to know that concentration of any product for a first order reactant at a first order will be equivalent to initial concentration multiplied by e raised power minus k t by this. Okay, so so similarly we can derive the concentration of B will be given by K1 A0 by K2 minus K1 so this will be concentration of B at a particular time. Okay, similarly we can correlate is 4 multiplied by 50 divided by 3 minus 4 exponential minus 2 minus exponential minus 1.5. It will be 17.6 mole per liter. So we got the concentration of B at particular time, that is T and this. Okay, also the concentration of A, we have determined the concentration of A. I already told you it will be equivalent to A0 E minus KT. Okay, that is given by 50 multiplied by E minus 2 is equivalent to 6.77 mole per liter. Okay, so the concentration of C will be given by A0 minus A minus B. Okay, so the concentration of the C will be 50 minus A plus B, which is given by 50 minus 6.77 that we have already determined plus 7.56. It is given as 25.67. So that is the answer to our question. Okay, so what we have determined, this is a consecutive reaction, and from the consecutive reaction what we have calculated is that at any amount of the time the total amount that is remaining of A plus B plus C should be equivalent to the total amount that was taken initially of A, because initially the concentration of B and concentration of C is constant, they are not existent. Okay, as the reaction starts, A gets converted into B and B gets converted into C. So once these happen, then what will happen is we calculated the concentration of the A at a particular time, that is after 0.5 seconds. Then similarly the concentration of B after time t, and then from that we can determine the concentration of the C. Okay, so that is now I will give a brief overview of what we have solved today, and what are the different here. Okay, first we had how the diffusion coefficient is dependent upon average velocity, and how it is dependent upon the mean free path. Okay, so from the mean free path we get to know about the diffusion coefficient. That was the first question. The second question was regarding the thermal insulation. Okay, we had to determine the heat flux where the thermal conductivity of the material was given. Okay, so we have used the fixed law to do that. Okay, then we have how the viscosity coefficient is related to the average speed according to kinetic theory of the gases, and density, and the molecular diameter as well as the molecular mass. Okay, so we know that viscosity will be inversely proportional to diameter and directly proportional to molecular mass. So from that we have shown that if the diameter of A is greater than diameter of B, then the viscosity of B should be equivalent to the viscosity coefficient of B should be equivalent to viscosity coefficient of the A. Then there we had the question regarding the thermal conductivity, in which we have shown that we have seen that thermal conductivity is directly proportional to the average speed and the heat capacity. Now if it's a monatomic gases, both we are comparing between two gases and both are monatomic, then heat capacity at constant volume will be almost same. Then we have directly average velocity. Since the average velocity depends upon the molecular mass, lower the molecular mass, higher the average velocity. So lower the molecular mass, higher will be the average velocity. Thus for monatomic gases, the atom which has the lower mass will have higher thermal conductivity. But if we have a diatomic gas or a monatomic gas, the diatomic gas has higher CV, so as a result the heat capacity of diatomic gas is higher as compared to that of diatomic. Why it is higher? It is because it has more degrees of freedom to absorb or to store that energy as compared to, because monatomic gas has only 3 degrees of freedom, it has only translational degrees of the freedom, but diatomic gases will have 2 multiplied by 3 multiplied by 2, 6 degrees of the freedom. Okay, so it can store energy in 3. Similarly, if you take a triatomic gas, it will have 9 degrees of the freedom. Okay, so it can store more energy. Okay, so then we had how we can convert a pressure gradient into a number gradient. We have used an ideal gas equation and then we calculated. Then we had to using that pressure gradient, we had to calculate the flux density, how much amount of the heat is flown from one form to the another form using this. So then we took the next assignment, that is regarding the reaction kinetics. I have briefly explained about the rate of the reaction and what is the units of different rate constants for different equations, and using the law of the mass action. And similarly we have a question second where we are having two products. One product is a thermodynamically driven product, another is a kinetically driven product. I have briefly told you how to determine that a product is thermodynamically driven and when it can be formed, and how a product is kinetically driven and when, under which conditions we'll get a kinetically driven product. Okay, then we had a reaction, that is a consecutive reaction, in which A was converting into B and it was converting into C. Then we had to determine at a particular time after the start of the reaction what will be the concentration of the C. That we have solved, because we know that the total concentration of all the products, all the reactants and all the products plus the initial reactant will be the total amount that was taken initially, that is the reactant A. Then using that equations, rate law equations, we have determined the concentration of reactants at different instants of different reactants. Then subtracting from the total amount of the reactant that was initially taken, we can determine the amount of the C. Okay, we have other questions in the meanwhile that probably that will be starting in the next. So thank you for today. We'll join in the next session and we'll solve more questions regarding the chemical kinetics and chemical thermodynamics. Thank you so much.